Every program requires memory to store data, but memory is a finite resource. Think of your computer's RAM like a physical workspace. When you start a task, you lay out your tools and materials. If you never clear the disk, you eventually run out of room to work. In software, we call this memory management. Historically, programmers had to decide exactly when to grab a piece of memory, and more importantly, exactly when to put it back. Today, we have two primary philosophies: manual management, where the developer is the architect, and garbage collection, where the system acts as an automated janitor. Understanding the friction between these two approaches is fundamental to choosing the right tool for your specific application's needs.
In languages like C and C++, you use commands like malloc and free to manage memory manually. You ask the operating system for a specific number of bytes, use them, and then explicitly tell the system you are done. This offers incredible performance and predictability because there are no hidden background processes cleaning up after you. However, it places a massive burden on the developer. If you forget to call free, that memory stays occupied forever. This is a memory leak. If you try to use memory after you've already freed it, your program might crash, or worse, become a security vulnerability. It is a high-wire act where the developer has total control, but no safety net.
Garbage collection, used by Java, Python, and Go, shifts this responsibility from the human to the runtime environment. The programmer simply creates objects, and the language's garbage collector periodically scans memory to find data that is no longer reachable by the program. The most common method is mark and sweep. First, the collector identifies roots, objects that are definitely still in use. It then follows every reference from those roots, marking everything it touches as alive. Finally, it sweeps through the rest of memory, reclaiming any space that wasn't marked. It's elegant and prevents most memory-related bugs, allowing developers to focus on logic rather than bookkeeping. But this automation isn't free. The garbage collection tax comes in the form of CPU cycles and latency. To accurately mark memory, many collectors must perform a stop-the-world event, where your entire application pauses so the collector can work without the data changing under its feet. For a web server, a 50-millisecond pause might be unnoticeable, but for a high-frequency trading platform or a competitive video game, that pause is a disaster. Modern collectors have become incredibly sophisticated, running concurrently with your code to minimize these stutters. But the overhead of managing the metadata for every object remains a constant reality.
So, which is better? Like most things in engineering, it depends on your constraints. Manual memory management is the choice for systems where every microsecond and every byte counts. Think operating system kernels, game engines, and embedded systems. Garbage collection is the choice for productivity and safety, powering the vast majority of business applications and web services, where developer velocity is more valuable than raw hardware efficiency. Interestingly, languages like Rust are now offering a third path, using ownership rules to provide the safety of GC with the performance of manual management. The goal is no longer just about cleaning up. It's about choosing the level of control you're willing to handle.